In the last topic, we introduced the chemist's way of counting. We introduced the mole. The mole is our convenient way of counting a very, very large number of items. If you have a mole of something, you have Avogadro's number of them. That's 6.022 times 10 to the 23 of them. What's that number based on? It's based on how many atoms you would have if you had 12 grams of carbon-12, something you can easily hold in your hand. So this mole, this new way of counting, how can we use it? How does it help us count out or measure out materials? Well, let's have a closer look. First of all, we're set for carbon. We know that if you have 1 mole of carbon, you have 6.022 by 10 to the 23 atoms, and that's 12 grams of carbon-12. So if you had half a mole, that would be 6 grams of carbon-12. If you had a quarter of a mole of it, 3 grams of carbon-12. Carbon's only one element on the periodic table though. We need to be able to work with all the others. Well, pull out your periodic table and have a look. In particular, let's have a closer look at the carbon atom itself, the one we've been talking about so far. Every time I've put one of these element tiles in front of you right throughout this entire subject, up in the top right corner I've left that red number. Haven't spoken about it until now, it's time. That number is actually going to be critical for the rest of our work together. That number there is called the atomic mass or the molar mass of the element, and you'll see it's there for every element on your periodic table. That number there is the average mass of 1 mole of that element in grams. So if I take 6.022 times 10 to the 23 carbon atoms, my periodic table tells me it will weigh 12.01 grams. And we now know this for any and every element. But let's go back for just a second. I'm sure you're looking at this number saying, hang on, 1 mole was based on 12 grams of carbon-12. Why is this one 12.01? Why is it different? To which I say to you, have you forgotten about isotopes? Do you remember what they are? They are the atoms which have the same number of protons, so it's the same element, the same type of atom, but a different number of neutrons in the nucleus. And that means they'll have a slightly different mass. If we take carbon as an example, if you take a random sample of carbon from anywhere in the world, you will find carbon-12, the one on the left. You will also find carbon-13, the one I've drawn in the middle, and you'll find carbon-14, the one I've drawn on the right. Maybe even very, very small amounts of some other isotopes. But these are the 3 most common. Thankfully, if you take any sample from anywhere in the world, the mix of those isotopes that you get is the same. You'll still get the same proportion of each isotope. Turns out that for carbon, it's about 98–99% carbon-12, and the other ones make up small but still known portions. When you average them all out, you end up with 12.01. So again, if you take any random sample of carbon from anywhere in the world, pick it up. If you measure out 6.022 by 10 to the 23 of those atoms, it would weigh 12.01 grams. So once again, that number is called our atomic mass, or we're going to refer to it as our molar mass. Why our molar mass? Because it's the mass of something in grams, your everyday measure of mass, that you would have if you had 1 mole of it. 6.022 times 10 to the 23 of it. And again, we know that for every element on your periodic table. For example, I've got some zinc here. I can tell from my periodic table, if I want 1 mole of zinc, I need to weigh out 65.37 grams. What if I had lead? If I wanted a mole, I'd need to weigh out 207.2 grams. Any element, we can immediately tell how much we need if we want a mole of it. Now we can see we're making some progress. We can see how we can use this, why it's helpful on a day-to-day basis. Let's take a hypothetical example. Let's say that you and I wanted to build some carbon monoxide, just carbon and oxygen chemically bonded together. In theory, we'd say, I want 1 carbon atom and 1 oxygen atom, and I'm going to join them together. But we know we can't do that. We need an even number of them. I've been saying to you, all right, let's start counting by the mole. But it's not really any easier to pick up 6.022 by 10 to the 23 of them if you're thinking about literally counting. But our molar mass, our atomic mass, allows us to relate this mole to a very easy, readily measured quantity. It allows us to use mass instead. Instead of saying, I want 1 atom of carbon and 1 atom of oxygen, I can say, I want a mole of carbon and I want a mole of oxygen. Using my atomic mass, I can then say, 1 mole of carbon, that's 12.01 grams. 1 mole of oxygen, that's 16 grams. And I can measure those masses out much, much more easily, a more common everyday measure. So now you can see how our new way of counting, the mole, could be incredibly useful for us. We're going to spend the next couple of topics building even further on this skill so that we can quantify all kinds of materials around us, no matter how much is there or what appearance it may have.